So we talked about the vector equation of a line. Now we'll look at the vector equation of the curves. Now, as far as the syllabus goes, and I'll show you that later so you can see exactly what it says, they're pretty much restricted to a circle. Obviously, there's lots of other curves you could have, but it's the vector equation of a circle that we're interested in. And it's a fairly simple one. If you think about it, it's obvious that this is the answer in 2 dimensions. What are we saying there? The absolute value of v minus v naught is equal to r. The length of the vector v minus v naught, so whenever we join v to v naught, always stays the same. So again, no matter where you place that point, you're going to get a circle. So what is the centre? Well, the centre is the v naught. So that's like the fixed point we know. And the radius is r. So it's simply that. I guess it's very similar to what we saw in complex numbers, isn't it? Where we said z minus z naught. Yeah. So it's the same idea. All right, well, let's just expand this thing out just to prove that it does indeed give us a circle. So it's head minus tail, so x minus x naught in the I direction, y minus y naught in the j direction. We want the magnitude of that. So you end up with x minus x naught squared plus y minus y naught squared is equal to the radius squared when you square both sides because you want to get rid of the square root sign on the magnitude. And yes, that is what we recognise as the Cartesian equation of a circle. Now I'm going to create the parametric equations. Starts from cos squared plus sine squared equals 1. We know that, of course. So I could say r squared cos squared plus r squared sine squared is r squared, just multiplying by r squared. Well, if I let x minus x naught be r cos theta and y minus y naught be r sine theta, rearrange that and we come up with the parametric form. So x is x naught plus r cos theta, y is y naught plus r sine theta. Well, let's write it as vectors, and there we have it. So there's that centre, x naught, y naught, plus r cos theta, r sine theta. R is fixed, theta in this case is the parameter. So as you substitute a different amount of degrees, the point will start moving around. All right, we're going to show that this is in fact a circle. Find its centre and radius. Now, it's been written in component form, but we still know that u dot u is magnitude of u squared, that idea. So that's what we've got here. So what I'm saying is the magnitude of r minus 2a plus 3j squared will equal 12. Find the square root of both sides. There's the vector equation of a circle. So the centre must be 2 minus 3, and the radius must be 2 root 3. We're going to find a vector equation of the tangent to this particular circle. Drawing a picture. There's our circle, x squared plus y squared is 25. I've drawn in the tangent at 3, 4. R is just some random point on our vector. So PR would be head minus tail. Whatever vector R is, position vector of that point up there, minus the position vector of P, which is 3i, 4j. Okay, we know the radius is always perpendicular to the tangent. Now, the position vector for P would be in fact that vector. It's joined to the origin. So OP is 3i plus 4j. But the radius is perpendicular to the tangent, therefore the dot product of each of these must equal 0. Well, I could expand the whole thing out, but essentially that has to be an equation for that vector. See, the only variable in all that is r, and r is the vector we're trying to find the equation for. All the others are constants. So yes, okay, I could expand the whole thing out, but I've satisfied it. They've said find a vector equation. Sure, it's not in the format that we saw yesterday, but that is an equation using vectors, and it perfectly describes that tangent. But what's the Cartesian equation of the tangent? Damn, thought I could get away without expanding. No, we're going to have to. All right, let's work out the dot product of these two things. So r, I'll give random coordinates x, y. And so the first one becomes x minus 3i plus y minus 4j. Dot product, x times the x's, y times the y's, 3x minus 3 plus 4y minus 4. And we eventually, there it is, 3x plus 4y minus 25 is equal to 0. There it is in general form. A sphere then. Remember I said circles? Well, that's 2 dimensions. Of course, we push it into 3 dimensions, it becomes a sphere. But the equation's exactly the same. Because we're using vectors, it doesn't matter. So it's still going to be v minus v naught is equal to the radius, but now it's the radius of a sphere, set a radius of a circle. Centre is still going to be v naught, and the radius is still r, because we're still essentially saying the same thing. The length of the vector joining v to v naught is constant. But now we're in 3 dimensions, so instead of scribing out a circle, it could go in any direction, so we scribe out a sphere rather than a circle. Let's go and find the actual Cartesian equation of a sphere then. So we'll do exactly the same thing. Well, we're saying that magnitude is equal to r. So x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to r squared. Very similar to the Cartesian equation of a circle, we've just added in the z components as well. So that would be a sphere. I won't even attempt to prove this right now. It's not too bad. You sort of start with the same idea, but we have to use 2 parameters. So you notice there's theta and there's phi as well. But that would be the parametric equation of a sphere, something like that. All right, we have 2 spheres. These 2 spheres intersect. Now, you've got to use your minds a bit here, but imagine getting 2 tennis balls, if you like, and they join together. If you were to sort of cut at the point where you'd end up with a circle when these 2 spheres touch. We want to know which plane will that circle be on. Well, fortunately the numbers are nice, because you'll notice that x plus 2 squared are in both, y plus 3 squared are in both, so these simultaneous equations will cancel quite nicely. Both the x and the y go at the same time, and I end up with z plus 2 squared minus z minus 4 squared is 9. Playing around with that, I get z equals 7 over 4. And that's an equation of a plane. So there's the plane, z equals 7 over 4. So what's the centre and radius of that intersecting circle that lies on that plane? Well, now we know z is always 7 on 4. I can substitute that into either the equations of the sphere that they gave me. So I've chosen this one. But we should end up with an equation of a circle. And there it is. X plus 2 squared plus y plus 3 squared is equal to 175/16. But you've got to be careful here. The radius, fair enough, I can work this out. But you've got to be very careful with the centre. Remember, you're not dealing with something in 2 dimensions here. You're dealing with something in 3 dimensions. So when we write the centre down, because we're in 3 dimensions, we need 3 numbers. So yes, the centre has an x value of -2 and a y value of -3, but don't forget the z value, the plane that it's lying on, of 7 on 4. And the radius, 5√7 over 4. This time we've got a sphere and a line, and we've got to find where they intersect. A sphere and a line. So what I've done is I've substituted the equation of the line into the equation of the sphere. That should be able to create what lambda will end up equaling and things like that. So let's play around with this. We're saying the magnitude of lambda I minus 2j plus 3 minus 2 lambda k must equal 4. Let's find the magnitude. So it'll be lambda squared, and then we've got 2 squared, so that's 4. And then 3 minus 2 lambda squared, there's the 9 minus 12 lambda plus 4 lambda squared. That's equal to 16. We've got a quadratic. We solved the quadratic. Well, no one said they were going to be nice numbers. So lambda is 6 plus or minus the square root of 51 on 5. We want to find the intersecting points. Well, I'm going to use the line. It's going to be easier to work out. It's not in column notation, but we can still read it. The x's will be 1 plus lambda. And so 1 plus, 6 plus or minus root 51 would be 2 possibilities. The y value, when we look at the equation of the line, look at that. There's only 2j, there is no other j, so y must always be 2. The z, now I'm looking at the k's, 3 minus 2k lambda. So 3 minus 2 lambda, I double my 6 plus or minus root 51. So the 2 points, there they are. One is 11 plus root 51 on 5, 2, 3 minus 2 root 51, 3 minus 2 root 51 on 5, and the other one. I can't read that all out. Why did I pick such horrible numbers? This example here comes from the sample paper that NASA put up before they'd done the first HSC. So to give an idea of what sort of questions might they ask. V is a position vector of a point P on a sphere S with centre C, radius R, and then they've given us the equation. Yeah, magnitude of vector V minus vector C is always R, so yes, it's a sphere, and C is the position vector OC. Do not prove this. Okay, I won't. The equation of the line L through the point P in the direction vector M. That's just a long way of saying the line is that. W, they've given it the letter W rather than the usual R, possibly so it didn't get confused with the radius maybe. So W is equal to V, a point on the line, and lambda M. M is the direction vector. Find the values of lambda that correspond to the intersection of the line L and the sphere S. The answer will be in terms of V, C, and M. I need a picture. Okay, got to try and understand what's going on here. There's the sphere. We've told V is the position vector on the sphere. Okay, so I've drawn that in. Centre C, so C is the centre. Okay. The vector goes through the sphere somewhere. W is this random point on the line. I've conveniently made it the other point of intersection on the sphere. We know that the distance from W to C is the radius. We know that. I'm going to substitute in the equation for W. So V plus lambda M minus C is equal to the radius. Well, I'm going to square both sides because that allows me now to use the dot product. So I can say that dot that is R squared, which gives me this lovely expression. Remember what we're trying to get here? We're trying to make lambda the subject of something because we want to find the values of lambda, and we're hoping our answer will have V, C, and M in it. I'm getting very close. Well, V minus C dot V minus C is the magnitude of V minus C squared. 2 lambda V minus C dot M, can't do anything with that. M dot M is magnitude of M squared. Okay. Whew, I've got to get rid of R somehow. Aha. There it is. Magnitude of V minus C. They've even told us in the question. Magnitude of V minus C is equal to R. So that becomes R squared, which will cancel with the R squared on the other side. We no longer have R, and the only pronumerals we have left, lambda, which we want, V, which we want, C, which we want, M, what we should now be able to make lambda the subject here. All right, let's play around with it. We've got a bit of a quadratic. Mind you, it's a simple quadratic because we've got a common factor of lambda. There it is. Lambda is either 0, I mean that's a possibility, or there's the expression 2m dot c minus v over the magnitude of m squared. We've satisfied the question. I'm not saying that's an easy question. I'm just saying that was the example of one they put in the sample paper. And it didn't finish there. Deduce that the line L is tangent to the sphere if, and only if, that expression is true. And then interpret geometrically. Well, what do we know? If it's a tangent, there's only one point of intersection. So in other words, remember I randomly placed it on the sphere? It now has to be at V. So W and V have to be the same point. Well, W, recall, was V plus lambda M. I'm now saying V plus lambda M is equal to V, which forces lambda to equal 0. Well, I already knew that. I've got that there. Well, how does this help me? Well, we're saying lambda can only equal 0. Therefore, the other one must be 0 as well. Okay, so if that's equal to 0, I've got a fraction equaling 0. It must be the top of the fraction that equals 0, which I can divide by -2, and I've got their expression. M dot V minus C must equal 0. Yes, an example of a question which would probably appear later in the paper, towards the end, I would imagine. But they're fun. And the geometrical result, what you have just proven, is that the tangent is perpendicular to the radius. Because you're saying M dot V minus C is equal to 0. M was the direction vector of the line. V minus C was the radius. So not only is it true in a circle, it's true in a sphere as well. Other common graphs in 3D. I'm going to show you some other ones. Remember, circle, sphere, that's pretty much it. But let's just look at some other shapes. Don't panic about them. The plane, oh, okay, fair enough. We should know the plane. We talked a bit about planes. But basically, planes are when the power of x, y, and z are 1. Now, the coefficients might be 0, because remember we had those planes like z equals 4 and things like that. But if the power of x, y, and z are 1 in that sort of sum, we know we've got some sort of plane. That would be a hemisphere. Remember the semicircle was the square root of the radius squared minus x squared, something like that? You get a very similar expression. One of the pronumerals, so I've made it z, will be the square root of r squared minus the other one squared. Now, depending on which one is the subject, tells you where the hemisphere is. So because I've made it z, you can see that it's sitting on the xy plane. Had I made it x equals the square root of r squared minus y squared minus z squared, then it would be sitting on the yz plane. And similarly, positive square root means it's above the plane, negative square root would be below the plane. A paraboloid. And this one has the opening in the z direction, so parallel to the xy plane. Z equals x squared plus y squared. A cone would look something like that. Z equals some constant times the square root of x squared plus y squared. Remember, you don't have to know these, it's fine. A hyperboloid. Hyperboloid of one sheet. So when there's one sheet, you'll notice only one of the squares is negative, because to get a hyperboloid of two sheets, two of them end up being negative. One of them negative, you get the inside surface. Two of them negative, you end up getting the outside surface. And we'll finish with the helix, a wonderful spiral. And whilst I say you don't need to know that, that was in last year's HSC. But there's your helix in parametric form. I've written it there, 3 sine 5t, 3 cos 5t, and t. 5G, and that finishes vectors.